welcome you all to session 2 of the chapter Frames of Reference. This session will be on Galilean transformation. Galilean transformation. Galilean transformation. We came to know that frames of references are of two types. One is inertial and another one is non-inertial. A frame of reference which is at rest or moving with uniform speed, then that kind of frame is called as inertial frame of reference, right? A frame which is moving with variable speed, which has acceleration, that kind of frame is called as non-inertial frame of reference. Non-inertial frame of reference is also called as accelerated frame of reference, where fictitious forces arises, but in inertial frame of reference there are no any fictitious forces, right? So these are some differences between inertial and non-inertial frames of reference, right? In short, in inertial frame of reference Newton's laws holds good, and in non-inertial frame of reference Newton's laws do not hold good. Now the next session is about transformation, right? So we are transforming the coordinates. So first we will be studying about what is the meaning of Galilean transformation. Okay, before that let us understand, if an event takes place at this point P, what is the meaning of event? Event means I am standing here, that is also an event, right? A car is moving, that is also an event. A train is standing at that place, that is also an event, right? Okay, let me take, let an event takes place at point P, and I am seeing that event from two frames of reference. First of all, let me take that from this frame. Let me consider it as x-axis, y-axis, and another one is z-axis. If I am considering this event, I am seeing this event from this frame of reference, right? So the coordinates of this event, let me take it as x, y, z. At a time t, let me take it as like this, x, y, z, t, right? So this is space and this is time. That is why these coordinates are called as space-time coordinates, right? Okay, so this is the position and the time at which this event takes place. So let me call it as p, x, y, z, t. So these coordinates are called as space-time coordinates. So this is the coordinates with respect to frame x, y, z. Okay, let me call this frame as yes. Okay, let me consider another one frame here, right? If I am considering this frame x dash, let me consider another one frame that is y dash. Let me consider another one frame that is z dash, right? If I consider this frame, and if I take this distance is nothing but, let me call it as x dash. This distance is, what is that now here? X. Sorry, this is x and this is x dash. If I want to write what are the coordinates at this point P from frame of reference, let me call this frame of reference as s dash. Then the coordinates will be x dash, y dash, z dash, and t dash. Or let me call it as x prime, y prime, z prime, and t prime. So these are the coordinates, right? The first coordinate is with respect to frame S, and the second coordinate is with respect to frame S dash. And if I want to relate these two coordinates, I will be using a transformation called Galilean transformation, right? For example, I am seeing this event from a petrol bunk. Let me call this origin as a petrol bunk, right? And this origin, let me call it as from bus stand here, right? So if I am seeing this event from a petrol bunk, right, that is the frame of reference which I am considering, right? That time the coordinate is x, y, z, and t. I am seeing the same event from a bus stand, then the coordinates are x dash, y, z, y dash, z dash, and t dash. And I am relating these two coordinates with the help of which transformation? Galilean transformation here, right? Okay, what are Galilean transformation? What is this transformation is all about? It is the transformation. It is the transformation of what? Transformation of what? These are the space-time coordinates. Space-time coordinates. The transformation of space-time coordinates of an event which takes place at the point P, right? Okay, the transformation of space-time coordinates of an event from one inertial frame of reference, from one inertial frame of reference to another inertial frame of reference. Another inertial frame of reference. Okay, see, the transformation of space-time coordinates of an event from one inertial frame of reference to another inertial frame of reference, this transformation is called Galilean transformation. This transformation is called Galilean transformation, right? So this kind of transformation of a coordinates from one frame of reference to another frame of reference is called Galilean transformation. And one thing what we need to remember is, here is, if one inertial frame of reference is moving at a constant speed, that speed must be slower, right? That should be having a low velocity. What is the meaning of low velocity? If I compare it with the velocity of speed of light in vacuum, if one of the frame is moving, that should move with a smaller velocity. Means in day-to-day life, we are finding the velocities which are smaller itself. The smaller velocity, if the car is moving, let me consider the smaller velocity when we compare it with the speed of light. So in day-to-day life, whatever velocity we see, those velocities are smaller velocity as compared to the speed of light in vacuum. If a frame is moving with that kind of velocity, we can consider the transformation called as Galilean transformation, right? Okay, now, so this is what actually the Galilean transformation is now here, right? Okay, now, so let us consider about how many transformation equations we can consider now here. Okay, let me take like this. For any instant of time t now here, right? For any instant, the space-time coordinates for any instant, space-time coordinates are different for different frame of reference. For different frame of reference. Okay, see here. For any instant, the space-time coordinates are different for different frame of reference. If you are going with the two different frame of reference, space-time coordinates will be different. The equations which relate these coordinates are called transformation equations. What we say now here? Equations. Okay, see here, what are transformation equations, right? The equations which relate the coordinates from one frame of reference to another frame of reference, those kind of equations are called as transformation equations. And these transformation equations are of two types. Okay, so we are relating these coordinates with each other. So the equations which relate these coordinates are called as transformation equations. Transformation equations are of two types. Let me take like this. Transformation equations are of two types. Okay, let me consider. There are two types of transformation equations. The first one is about Galilean transformation equations. And the second one is about Lorentz transformation equations. Okay, so when to use Galilean, when to use Lorentz, let us understand here, right? If one of the frame is at rest and another frame is moving, right? If the frame is moving with lower velocity, that time we will be using Galilean transformation equations. Okay, so these equations are used if frame is moving, if the frame is moving with low velocity. Do you understand? If a frame is moving with low velocity, that time we will be using Galilean transformation equation. Right? If a frame is moving with low velocity, means if a car is moving now, right? In the car itself, we will be considering x-axis, y-axis and z-axis. If the car is moving with a velocity which is very less as compared to the speed of light, of course, in day-to-day life, the velocities, whatever we see, are low velocity itself. Right? So if a frame is moving with low velocity, that time we will be considering Galilean transformation equation. Right? If frame is moving, if frame is moving with high velocity. If the frame is moving with high velocity, that time we will be considering Lorentz transformation equation. High velocity means the velocity of the frame must be comparable with the speed of light in vacuum, right? If that much speed, if the frame is moving, that time we are not considering Galilean, we are considering Lorentz. So this session will be on Galilean transformation equations, and we will be deriving these Galilean transformation equations now. Now let us move on to the Galilean transformation equations. What are these equations? These are the set of equations. The set of equations which relate the space-time coordinates, which relate the space-time coordinates of an event. Okay, see here. The set of equations which relate the space-time coordinates of an event with respect to two inertial frame of references. With respect to two inertial frame of references having a relative motion between them. If they are having the relative motion between them, then these set of equations are called as Galilean transformation equations. The set of equations are called Galilean transformation equations. Galilean transformation, let me consider it as equations. Okay, now what are Galilean transformation equations? So first of all, they are the set of equations, right? So these are the set of equations which relate space-time coordinates of what? Of an event with respect to two inertial frame of references. And how should these inertial frame of reference should be? They should be moving with relative motion with each other. As earlier I said that Galilean transformation are the transformations we will be using when the frame is moving with low velocity. Means a frame is moving with a velocity which is very small compared to the speed of light, right? If the frame is moving with lower velocity, that time we will be considering Galilean. If the frame is moving with higher velocity, we will be considering Lorentz equation, right? So that is why we have considered here is that the two frame of references must be having relative motion between them here, right? That time the set of equations which relate the space-time coordinates are called as Galilean transformation equations. So what are those equations? Let us derive. The next is about derivation of Galilean transformation equations. Okay, now let us derive these equations. The next concept is about the derivation of Galilean transformation equations. After knowing what are Galilean transformation equations, let us derive those equations. That is derivation of Galilean transformation equations. So what are these equations? So that is Galilean transformation equations. Right. Now let us consider an event takes place at point P now here, right? And we will be seeing that event from two different frames of reference. So let us consider this is a frame of reference. Let me consider this is a frame. Let me consider this is as x-axis and this is y-axis and this is what we say here, z-axis. Let me call this frame as A, and an event takes place at this point now here if I'm considering, right? So I'm seeing this event from this frame of reference, and what is that frame of reference? That is S now here, right? So to derive Galilean transformation equations, we need two inertial frame of references. One let me call it as S and another one let me call it as S dash, right? Okay. Now I'll be considering another one frame of reference, right? For example, let me consider another one frame of reference, that is y dash, and this is x dash, and this is what we say here, z dash, and let me call this frame of reference as S dash. Okay, now let me begin with this here, right? First of all, let us write what are these. So consider two frames of reference. Consider two frame of references S and S dash with origins. So let me consider this as origin O, and let me call it as this as origin O dash, with origins O and O dash respectively. Okay, consider two frames of reference S and S dash with origins O and O dash respectively. Now these two are the frame. Now let me consider one frame is at rest, another one frame is moving now here, right? Okay, before that let me consider both the frames are at rest at the initial time now here, right? Okay, let me consider like this: at time t equal to 0, right? So at the time t equal to 0, both the frames are at what we say here, rest. Let me consider at the initial point, right? Later on I will move one frame with respect to other, but at the beginning let me consider both the frames are at rest. So let me consider like this: at the time t equal to 0, both the frames are at rest, so that origins O and O dash coincide with what we say here, each other. Let me begin like this: at time t equal to 0, both the frames are rest, so that these origins O and O dash coincide with each other. For example, I have already told you, one frame I will be taking at rest, and one frame let me consider it is moving, right? So it is moving with a uniform speed. Let me consider that speed. Let me call it as V, right? Okay, let me consider this is at rest and this is moving now here, right? But I will be considering a time t equal to 0. Let me consider this is moving from this side to this side. When this frame is moving from that side to this side, and there is a time at which O coincides with O dash, right? Let us assume this frame is moving now here, right? Okay, this frame is not here. It is moving with uniform velocity v now here, right? When it is moving from this side to this side, there is a point at which O coincides with what we say here, O dash. If O is coinciding with O dash, that time I will be considering the time as t equal to 0 here, right? Okay, the condition is that x must be in line with x dash, right? Okay, I already took here, so there should be one axis which are in line with each other. About y axis, they should be parallel, right? So y should be parallel with y dash, and z should be parallel with z dash. So these are the conditions, right? X should be in line, y should be parallel to y dash, and z should be parallel to what we say here, z dash, right? This is a moving frame which moves with velocity v. But at a time t equal to 0, for example, if I am considering at a time t equal to 0, y dash coincides with y, and x coincides with x dash, z coincides with z dash, and O coincides with O dash. This position we will be calling the time t equal to 0, right? That is what I have written here. At time t equal to 0, both the frames are at rest, right? How are they at rest? So that origins O and O dash coincides with each other. If O and O dash coincides with each other, of course x and x dash coincides, y and y dash coincides, z and z dash also coincides with each other. At that time, let me consider time t equal to 0, right? Okay, for example, if there is a S frame whose time is t, right, and there is S dash frame whose time is t dash, when they coincide with each other, I will be starting it from 0 now, right? If I am taking a stopwatch, I am standing here in frame S, and the time is t. There is my friend who is standing with the clock whose time is t dash. Let me consider like this. At this position, right, we will be starting with the stopwatch now, right? So at this position, let me consider t equal to 0 now here, right? Okay, first let us consider what happens when time t equal to 0. Now, when time elapses, what happens now here, right? As the frame is moving, let me consider this frame is moving. Now it is not at this position. Now the frame is moving. Let me consider this frame is moving, and that frame comes to this position here. Let me consider this frame is moving and it comes at this position x dash, and let me consider y dash, and let me consider z dash. Z and z dash parallel. Yes, they are parallel. y and y dash parallel, and x dash are in line with each other. And let me consider as yes, this is O dash, this is frame S, and this is frame S dash, which is moving with the velocity v here, right? Okay, now let me consider this situation here, right? If frame is moving, okay, frame, which frame is moving now here? Let us consider S dash. If frame S dash is moving with uniform velocity, if the frame is moving with uniform velocity, what is that velocity? V. And an event takes place at point P. Okay, see here. If frame S dash is moving with uniform velocity V and an event takes place at point P. Okay, let me consider this is a point P and an event takes place. Right? Okay, consider the point P, that is itself is an event now, right? Okay, now I will be writing coordinates of point P with respect to this frame of references, right? Okay, let me take now here. Coordinates of P with respect to frame S. Okay, let me consider coordinates of point P with respect to frame S. Okay, let me write here. I need some space to write that. Let me consider like this. Coordinates of P with respect to frame S. So what are the coordinates? Okay, with respect to frame S, the coordinates, let me call it as X, Y, Z and T. Right? Okay, if I am considering this is the point, so what is this distance? Let me consider this distance as X, and this distance let me consider it as Y, and this distance let me consider it as Z. So let me consider this is X, Y, Z, and the time, let me consider the time T for this frame of reference. So what is the coordinates of P with respect to frame S? X, Y, Z, and let me consider it as T. Right. Similarly, let me write what are the coordinates of P with respect to frame, what we say here, S dash. What are the coordinates of P with respect to frame S dash? So what are the coordinates? X dash, Y dash, Z dash and T dash. So what is X dash? So this is the frame S dash. So let me consider if this is and this distance, let me call it as what we say here, X dash, and this is Y dash and this is Z dash here, right? Okay. The coordinates of P with respect to frame S dash is X dash, Y dash, Z dash and T dash. Okay, we got two space-time coordinates and we will be linking these two coordinates, and the equations what we get are Galilean transformation equations. Okay, now let us move forward now here. Okay, after knowing these coordinates, let me find what are the equations which relate these coordinates X, Y, Z and the time T here, right? Okay. Let me consider this is the point O now here, right? Okay. Now what are the equations which relate X and X dash, Y and Y dash, Z and Z dash and T dash? Okay, let me check it out that now here, right? Okay. Now if I am considering from figure, let me considering from figure. Okay, from figure let me take like this. So this is the frame X and this is X dash now, right? From figure let me take like this. O dash plus O dash A is nothing but what now here? OA. Let me consider like this, right? Okay. From figure, OA is equal to, what is OA? This is OA. OA is equal to O dash plus O dash A. Okay. O dash plus O dash, what we say here? A. Right. Come on, tell me, what is OA? OA. What is this distance? This distance is nothing but X here. Okay. Let me consider X, that is equal to O dash. What is the distance O dash? We don't know. Let us find that now here, right? Okay. If this frame is moving with velocity, what we say here? V. Earlier, when these two coordinates coincide, that time we called as T equal to 0, right? At time T, it came to this position here, right? At time T, it reaches at this position, and this distance, let me call this distance, right? We know what is the formula for velocity. What is the formula for velocity? Velocity is equal to displacement divided by time, right? So what is the displacement equal to? From this I can write displacement equal to velocity into time, right? Displacement equal to velocity into time. If you know the velocity and if you know the time, we can calculate the distance. This is what I am doing here. Now let us find what is the distance O dash. If this is frame is moving with velocity v in time t, then the distance is velocity into time. So what is the velocity? V. What is the time covered? Let me call it as t now here, right? So what is the distance O dash? O dash is distance vt. Now I'll be using there. Okay. What is O dash? That is v into t plus. Come and tell me what is O dash a? O dash a is nothing but what we say here? X dash. Right. What is x dash equal to? That implies x dash equal to, if I am taking this to this side, x minus what we say here? Vt. So this is the first one. Let me call this equation as first equation. X dash equal to x minus Vt, right? So this is the first Galilean transformation equation along x axis. So that is x dash equal to x minus Vt now here, right? As there is no relative motion along y and z axis. So I consider that the frame S dash is moving with velocity v along positive x axis, right? Now there is no relative motion of frame S dash along y and z axis. It is not moving along y axis as well as it is not moving along z axis. That time I can consider it as y dash equal to y. It is not changing because it is not moving along y axis. And z dash equal to z, again it is not moving along z axis, right? So x dash equal to x minus vt, y dash equal to y, z dash equal to z, right? Let me consider this is equation number 2 and let me consider this is equation number 3 now here, right? Okay. As time is considered to be absolute in nature, absolute in nature. What is the meaning of absolute? That is, time does not change, or let me take now here, that is, time remains same in all inertial frame of references, all inertial frame of references. Okay, let me consider. As a time is considered to be absolute in nature, that is, time remains same in all inertial frame of references, we can say t dash equal to t. This is equation number 4. Okay, see, if I am considering the relationship between the space-time coordinates and as time is considered to be absolute in nature, means the time will be same in all inertial frame of references, right? If I take t and t dash, both will be equal, right? Because time is absolute in nature, it is invariant, it will not change with the change in inertial frame of reference. That is, what is the meaning of absolute in nature? Time remains same in all inertial frame of reference. That time let me consider t dash equal to t, right? So these 4 set of equations, let me call now here equations 1, 2, 3 and 4 are called, these equations are called Galilean transformation equations. These equations are called Galilean transformation equations if the frame S dash is moving with velocity v along positive x axis. So these 4 equations are called as Galilean transformation equations. Now let us see some note points about Galilean transformation. Let us take some note points. First one, 3 fundamental quantities, 3 fundamental quantities, length, mass and time are invariant under Galilean transformation, Okay, see here, there are 3 physical quantities, 3 fundamental physical quantities, length, mass and time are invariant under Galilean transformation. Invariant means they are not changing when inertial frame of reference change, right? If you change from one inertial frame of reference to another inertial frame of reference, length will not change, mass will not change, and the time will not change, and they remain the same. That is why I called it as they are invariant under Galilean transformation, right? So let us see some other physical quantities. Velocity. Velocity is variant. It changes with change in inertial frame of reference. Velocity is variant, whereas acceleration and force are invariant under Galilean transformation. Under Galilean transformation. Do remember this, right? Velocity is variant. Velocity changes from one inertial frame of reference to another inertial frame of reference, whereas acceleration and force are invariant under Galilean transformation. We will be proving this also, right? So first of all, we need to know that which physical quantities are variant and which physical quantities are invariant. Length, mass and time are invariant, acceleration, force are invariant, but velocity is variant with the Galilean transformation here, right? Okay, now let us prove length is invariant under Galilean transformation. Okay, now let us take two inertial frame of references. Okay, let us take the first one. This is the first frame of reference. Let me take axis as x, y and z now here, right? So this is a frame S which is at rest, and let me take another frame whose coordinates axes are x dash, y dash and z dash, such that y is parallel to y dash, z is parallel to z dash, and x is in line with x dash. Now this frame, let me call it as s dash, and it is moving with uniform velocity v along positive x axis now here. Okay, let me show that now here. Let me write about this. Consider two inertial frame of references. Inertial frame of references S and S dash, such that S is at rest and S dash is moving with the uniform velocity. S dash is moving with uniform velocity v along positive x axis. Okay, let me begin the derivation like this. Consider two inertial frame of references S and S dash, such that S is at rest and S dash is moving with uniform velocity v along positive x axis. Now I need to prove that length is invariant, right? So S is at rest, it is not moving, and let me take origin as O and let me take origin as O dash here, right? So this is at rest and it is moving with uniform velocity, right? So I need to prove length is invariant. So let us take a rod whose length is L now here. Okay, let me take a rod in S dash frame here. Okay, this is a rod. Let me take this as a rod now here, right? I want to find what is the length of the rod, right? If I see this rod from the frame S, so what we will be getting? Let me take this point. Shall I call this point as x1? So let me call like this. This is, I am measuring from a S frame. So at this point I need to measure it. So let me take x1 be the distance from O to this side of the rod, right? At that end, let me take it as x2, right? Till here at this end. So let me call it as x2. This is x1 and this is x2. Come on, tell me, what is the length of the rod? Length of the rod is x2 minus x1, right? This is x2 minus x1 gives length of the rod with respect to frame S, right? Okay, so that is how I'll be continuing with the derivation. I need to find the length of the rods. Okay, now let us find what is the length of the rod now here. Okay, let me take like this. What is the length of the rod? Length of the rod. Let me take length of the rod is L. So what is the length of the rod with respect to frame S? That is x2 minus x1. x2 minus x1, that is with respect to frame. Which frame? S. right? With respect to frame, yes, from I am saying from this frame, then what is the length of the rod? I measure it as x2 minus x1. If I am in this frame, right, this is a moving frame. From this frame, if I observe this, what do I get? Right? Okay, for example, from this frame I am measuring, so let me call this distance. Okay, let me call this distance let me call it as x1 is this distance, right, this end. Let me take x2 as this distance, x1 dash, let me call x2 dash, because I already use x1 and x2. x1 dash, so this is x1 dash and this is x2 dash. This I am considering with respect to frame s dash. Come on, tell me, what will be the length of the rod with respect to frame s dash? x2 dash minus x1 dash, right? I am measuring the length of the rod with respect to frame s dash here, right? Okay, let me call that length as L dash. Okay, let L be the length of the rod with respect to frame S. L dash is the length of the rod with respect to frame S dash. Okay, what is the length of the rod now here? x2 dash minus x1 dash. x2 dash minus x1 dash. Let me take x2 dash minus x1 dash. This is the length of the rod with respect to frame S dash, which is moving with velocity v along positive x axis now here, right? So I got the length of the rod with respect to both the frames. Now I need to prove that length is invariant now here. So I will be using Galilean transformation equation. Okay, let me use using Galilean transformation equation. What are Galilean transformation equation? If a frame is moving along x-axis, we know Galilean transformation equations. So what are Galilean transformation equations? X dash equal to x minus vt, y dash equal to y, z dash equal to z, t dash equal to t. So what are these? These are called as Galilean transformation equations. Since it is along x-axis, I will be taking this equation here. Shall I use this? That is Galilean transformation equation. For x2, I will be using first x2 dash equal to, what shall I take now here? x2 dash equal to x2 minus vt, right? x2 dash equal to x2 minus vt. What is x1 dash equal to? x1 dash equal to x1 minus vt. I have used this equation, right? So that equation I have used here, Galilean transformation equation, right? So do remember, these equations are called as Galilean transformation equation that I am using to prove length is invariant. Okay, now shall I substitute? Shall I say quick now here? Now, okay, what is L dash? Shall I take this? L dash equal to, what is the formula for L dash? x2 dash minus x1 dash. This equation I have taken here. What is x2 dash? Shall I substitute this? x2 minus vt minus, what is x1 dash? x1 dash is, what is x1 dash here? x1 minus vt. Shall I take like this? Okay, what do you get now here? That is equal to x2 minus vt minus x1 minus into minus plus, what do you get now here? Vt. So vt, this minus vt plus vt get cancels. What do you get now here? x2 minus x1, right? You got it, x2 minus x1. What is x2 minus x1? This x2 minus x1 is nothing but that is equal to L. Means, shall I end like this? Right? So that implies L dash equal to L. What is the meaning of L dash equal to L? Therefore, shall I say length does not change here, right? Okay, length is what we say here? Invariant, means it is not changing here, right? From frame of reference, yes, from frame of reference, yes dash. If you see, the length of the rod remains same. That is what I have proved here. That is L dash equal to L here, right? So since L dash equal to L, length is invariant under Galilean transformation, right? This is how we need to prove length is invariant under Galilean transformation, right? I took two frames by this. I took the length of the rod by this. I have seen the length of the rod from frame S1, then the frame S, and then frame S dash. I proved that L dash equal to L. Thus, I concluded that length is invariant under Galilean transformation. So this is the proof that length is invariant under Galilean transformation. Now, let us prove that velocity is variant under Galilean transformation, right? So this is the proof of velocity is variant under Galilean transformation, right? Question may be asked like this: show that velocity is variant under Galilean transformation. Okay, let us prove that now here, right? Again, as it is Galilean transformation, we need to take two frame of references with the axis x, y, and what we say now here, z. The frame is s with the origin O now here, right? Let me take another one frame. This frame is a moving frame. Let me take it as x dash, and let me take it as y dash, and let me take it as z dash with origin O dash. And this frame is s dash, which is moving with velocity, what we say here, v, such that x and x dash are in a single line, and y dash are parallel to each other, and z and z dash are also parallel to each other. Considering all this, let us start with the derivation here, right? Show that velocity is invariant under Galilean transformation. Okay, let me begin with the derivation. That is, consider two frame of references. Consider two inertial frame of references. Two inertial frame of references. Consider two inertial frame of references, s and s dash, such that s is at what we say here, rest, and s dash is moving with uniform velocity. It is moving with uniform velocity v along which axis? That is positive x axis. Just it is the beginning now here, right? So I have told you what I have drawn. Consider two inertial frame of reference s and s dash such that s is at rest and s dash is moving with uniform velocity along the positive x axis. Now let me consider here, right? Okay, just an introduction about the diagrams which I have drawn here, right? Okay, now let me begin with the derivation here, right? Okay, what I will be taking here is, I need to speak about the velocity. So I will be considering an event here. Okay, let me consider this is a point, and this point is moving along x-axis, right? Okay, if this particle is moving along x-axis, let me consider u, because I already considered v as the velocity of the frame. Let me consider a particle which is moving along x-axis. Let me consider it is moving along x-axis itself, right? So if I see with respect to frame s, let the velocity of the particle be u. Okay, velocity of the particle be u with respect to what we say now, frame s, and u dash with respect to frame s dash. Okay, I am considering a particle is moving along x-axis. What is its velocity? Its velocity is u with respect to frame s. I am seeing from frame s, the velocity of the particle is u. If I am seeing the particle from frame s dash, the velocity is what we say here, u dash. Now I need to prove that the velocity is variant. Okay, in order to prove, let me tell what are this now here, right? Okay, let u be, what is that now here? U be velocity of a particle, velocity of a particle, right? Let u be velocity of the particle with respect to what we say now here, frame s, and u dash be, velocity of the particle with respect to frame, what we say now here, s dash, right? Okay, let u be velocity of a particle with respect to frame s, and u dash be the velocity with respect to frame s dash. Now shall I use Galilean transformation equation? Yes. Okay, let me write down here, using what we say now here, Galilean transformation equation. Using Galilean transformation equation. What is Galilean transformation equation? If the frame is moving along positive x-axis, Galilean transformation equation is x dash is equal to x minus vt, right? So this is a Galilean transformation equation. What I will be doing, this is the distance, I want velocity. What shall I do? Shall I differentiate it? Because we know that dx by dt is equal to v now here, right? Okay, what I will be doing, I will be differentiating with respect to what we say now here, time t. Okay, shall I differentiate with respect to time t? What is the, shall I take like this, dx dash divided by dt, that is equal to, what is differentiation of x? Dx divided by dt, right? What is the differentiation of minus vt? That is minus v, right? Differentiation of dt by dt now here. So what is the differentiation of vt with respect to t is v now here, right? Since it is minus vt, I have taken it as v. Come on, tell me, what is dx by dt? Differentiation, right? So dx by dt is nothing but what? v dash, because velocity with respect to frame s dash no here, right? So sorry, not v dash, it is u dash, because it is the velocity of a particle now here, right? Okay, u dash is equal to, what is the velocity from with respect to frame s? That is u, minus, what shall I say now here? That is v, right? By this, shall I say like this? By this, I can conclude that u dash is not equal to u. That's true, right? U dash is not equal to u, means both are not equal. By this, I can say that, therefore, what is variant? Velocity is variant, because it is not equal. That is, velocity is variant under what we say here, Galilean transformation. Okay, this is the proof that velocity is variant under Galilean transformation, right? So thus we proved that length is invariant and velocity is variant under Galilean transformation, right? The question may be asked like this: derive Galilean transformation equations and show that length is invariant, and show that velocity is variant. If the question is asked for 5 marks, so this is the answer for that, right? Today we have learned the derivation of Galilean transformation equation and proved length is invariant and velocity is variant under Galilean transformation, right? Thank you.